Hello and welcome, everybody. Good morning, good evening, good afternoon, and thank you for joining to this final episode of this training series in March. Special, and I thank you, and very welcome to Claire. Thank you for joining us today and for giving us the workshop or guiding us through the workshop today. Hello, Claire. How are you doing?
Hello, I am well. Thank you for inviting me.
Yeah, that's it's very cool. It's the final episode today after we started with an intro and with a Blooms session, and last week we had Will giving us an overview of the GraphQL library integration. Now today we talk a little bit about data science and why graph database makes sense versus a classical SQL setup for data science. Before we dive in, I'd like to say a few things about the technicalities. We will record this session, obviously. So if you are wondering if you can watch this later or if you can share it with colleagues or some other things, obviously we will share a link with you where you can find it and where you can watch it afterwards. We will also make available slides and any links in the video description or in the video in the email as I'll be sending you as a follow up. So everything will be available for you. If you have any questions during this training series, we'd like to make it somewhat interactive. So please type it in. We have a Q&A section in Big Marker you can use to ask your questions. It will be obviously we will monitor them. Some we will take on live on stage basically, and some we will just answer you in written form. If your if a question cannot be answered in time, then don't be sad. Maybe you can take it on to our community, and somebody will help you there. We have a Discord server with lots of people there. We have a forum, so if you go on community.neo4j.com, there's plenty of resources for you for help on any question you might have. Yeah, and I think that's what I had to say about this. So yeah, today graph databases versus SQL for data science is the topic, and the question we want to ask, for lots of people ask themselves, is why would I want to use a graph database in the first place? I can do everything in SQL just fine, and I think we're going to learn today why that is just not true, and why that is somewhat more difficult if you think about it. And yeah, we had a few questions, I think, right? And, like Claire, in the polling section. So shall we
Mhm.
start with the poll as a start before
Yeah,
we
let's do
before we
that.
go? Yeah.
Let's do that.
All right. So I'll take the click on the first questions. Click on start. So you should get a pop up now asking you what's your current level of experience in data science slash machine learning. You have a couple of sections to select from. Obviously, if you watch this on YouTube or somewhere else, you cannot answer the question. But yeah, if you watch this with us in Big Marker, you should see it, and I'll see questions come in, or answers rather. So let's give it a few more seconds. Anything else you'd like to say while we collect answers, Claire,
Well, I
about today?
do want to warn people that the internet universe is not being kind to us today. We're going to be using a GitHub repository for the code in the live coding portion of the workshop. And GitHub, for those of you who use it regularly, you know it's been having some reliability issues, and this morning is no exception. Also, my internet service provider is not providing me the service that I expect, and my upload speeds are kind of slow today and all over the place. So I'm going to be turning my video off for part of this, but just know that there might be some sound cutouts, and Alex is going to be jumping in if that happens. And if I drop out for a few seconds, we'll go back and repeat what I had to say, and hopefully everything works out.
So far it works well, but you never know with these kinds of things. So yes, be a little bit patient if it comes to that. So I think we have fairly good amount of of answers. So I'm gonna close the poll now. Um, what we had was, can I actually share this somehow here? I don't think I can. It would be nice if I could, but I can read it to you while I open the other one. The other one is, what's your current level of experiences with the Neo4j Graph Data Science Library? So I'll launch that, and while I do that, we can go through the answers. So the 34% of people said, I'm not a data scientist but work with them. So we have a good amount of people that is more curious than hands-on.
Awesome.
But followed right away with 29% is, I'm studying data science. So people are students or learning about data science in some kind of academia or a learning platform.
Well,
And
we've
then
got some good
also,
stuff for you guys today,
yeah,
for y'all
uh,
today.
and also super close behind, 25% is, I'm working as a professional data scientist. So that's obviously uh, the experts here um, on the field.
Nice.
Okay, let me see. The other one is also seeing. I think I can close it as well. Um, so the current experience with the Neo4j Graph Data Science Library is, with majority of 55% of people said, I have heard of it but haven't tried it. So I think there's lots of interest in it, but not much experience.
Good.
So good, yes. And followed by that, with somewhat of a step behind, is 24% is, I have been learning how to use it, trying it out. So also it's a good, so newbies, but also tried experience. And then the next behind that is already 14%, so it's getting really low numbers now. I have not heard of it before, so that's also fine. So we'll explain what it is, what it does, and how it works today. Um,
Excellent.
yeah,
Excellent. Excellent. I think there's something for everybody in this talk.
yeah,
All right, cool. Shall we get started with the content?
sounds good. Let's get going. I'll be there. I'll be here. If anything happens, I'll jump in. But yeah, everybody enjoy, have fun, and like I said, make it interactive. So if you have questions, if anything comes up, let us know and type it in the chat so yeah, we can make it work. Good.
Great. Let's do it. Okay. I just want to start by saying thank you to everybody who's tuned in today. Good morning, good afternoon, good evening. My name is Claire Sullivan, and I'm a data science advocate at Neo4j. And I am speaking to you today from high in the mountains of Colorado in the US. Specifically, I'm at 10,200 feet or 3,100 meters, depending on your unit of choice. And just as a reminder, I am having some internet issues today, and that's fine. We are going to dive into some slides here, and I'm going to share my screen. I'm going to turn off my camera and hopefully not have a problem with my internet speeds. So let's do this. I'm going to share screen now. And you're going to see the infinite window here for a second. And I'm going to go to my slides. Okay, Alex, are you seeing my slides now?
Yes, I see your slides, and everything looks good.
Perfect. Okay, so today we're going to talk about the idea of comparing SQL and Neo4j and when you might use one over the other, when you might think about you having a graphy problem. And, this graphy I put in quotes here, you're going to hear that word come up quite a bit. And the idea here is that in data science and machine learning, we have a lot of problems that come up that we don't necessarily recognize would be solved better with a graph. So we're going to talk about today how you might recognize that and why, if you do have a graphy problem, it might benefit you to move out of SQL and into Neo4j or some graph construct. I will tell you that given the way that Big Marker works, I cannot see the question window. Please type your questions in there. We do have some proctors in the room who will be helping answer them. We will ideally have a break at some point here, and I'll be looking at the questions in the window and work on answering them. And again, I do want to mention that Discord server, which is a great place. Like if you have a question that doesn't get answered or you think of one later, please go there. Okay, now the most important questions. In case you missed Alex's start, this workshop is being recorded. So if you want to see the video afterwards, if you want to share it with people, cool, it'll be there. So then we will have a repository for the code. We're going to be doing some live coding today, and you're welcome to code along. You're welcome to watch, whatever. It's all good. And I'll be showing the link to the repository several times during this talk. And then all of the slides themselves are available within the repository. Okay, so I just wanted to start with when I looked at what was happening with the internet today, what was happening with GitHub being very unreliable today, I was getting a little nervous here. So I wrote a nice little SQL query to describe nervousness. It's actually not mine. I open sourced it from the internet, but I think it describes where we're going to go today. And hopefully the internet universe is going to be kind to us. Okay, so what are we specifically going to do? The number one question I get asked pretty much at every single talk, presentation, workshop I give is, all of my data is in SQL. Why would I bother with a graph database? I mean, if you think about it, you're taking on some overhead in doing so. You have to think about, how do I get my data in there? I'm going to need to support it. As data scientists, we're pretty familiar with SQL. Probably a lot of us have worked with it at some point or another. Why do I want to learn a whole new query language even? And then, do I even need to? Do I even have a data set that would lend itself well to this graphy problem? Um, so we're going to talk about today why graphs, why solving problems in a graph paradigm, graph data structure, why that might be better than a table like a relational database provides. When we're going to have a live coding session here. Like I said, we're going to be doing part of it in SQL and part of it in Neo4j, and then we'll wrap up. Okay, I mentioned that there's a repository for the code. This is the link to the repository. I will put this up several times, but this is going to take you hopefully to my GitHub, where you can get all of the code, the slides, everything. Okay, I like to start all of my talks with what I call two key concepts. And what this is if you take away absolutely nothing else from today, these are the two things that I want you to remember. The first, it's not always obvious that you have a graphy problem, but you should look at whether the importance of the relationships between your data, whether that matters. And one hint for this is that if you have a lot of SQL joins, you probably have a graphy problem. Now, the second thing is that when you have a graphy problem, it's easier and faster to solve it in a graph database rather than an RDBMS, a relational database. Okay, this is kind of a question that I've received before. All of my data is all in BigQuery and scattered among several tables. I'm trying to answer a question about our users, but the query takes forever. And so then my follow-up question was, well, how many queries do you have? How many joins do you have? Well, there are a lot. Okay, so this is a common problem that we face as data scientists. Is just some of these SQL queries can take a long time. Even if you've got some nice Presto cluster or something sitting there waiting for you, they can get pretty complicated. So let's look at how complicated can they get. And I'm going to go through some standard SQL queries here. Now, in only 2 hours, we can't possibly go through every single SQL scenario. So I'm just going to try and hit some big ones. For those of you students in the room, these type of questions do come up in interviews. So you can very well act, if you're doing some sort of live coding, whiteboarding or whatever in your interview, that you'll be asked these big O questions, big O notation. Okay, so here's just a simple select. I'm going to count all of the entries within some table here. This query is order 1, so that's great. That's perfect. That's a really nice order. Assuming that you have a primary key, assuming you've set up your database, your tables with a primary key. Next one, let's say I'm wanting to search for a particular user within my database. If I've got some table called user. So what this is going to be, I have to search through all of the entries within that table. So that implies that we have a big O of n, where n is the size of my table. Okay, that's not as good as order one. It's not horrible. Let's look at this one here. Let's say I have a hash join, and this is where you have projections of the joined tables that are not already sorted. Merge joins are faster, but let's just say this is a hash join. And so I've got two different tables here. I've got users and I've got posts, and I'm joining on them on some sort of ID, and I'm specifying a few requirements here. And so this is starting to get a little slower now. Okay, so if I have N is my hash table, M is my lookup table. My order is N plus M. So you can see as those tables are getting bigger, and those of you who work for some companies where you have really big tables, this is going to be problematic, right? So, you need to start, as you're asked students about queries across tables, think about query sizes here. Now, just really quickly, if you were doing a merge join, this is actually a little better. I don't have it on this slide here, but it's order n times log n plus m times log m. And that's if neither table has an index on the joined table or the joined columns. Okay, so just always think about your order is generally going to have to do with the size of the tables. Okay, let's see what our next one is here. This is, let's see, this is, we've got users. We're going to select one column from user, one column from comment where those user IDs are the same. And, we've given a few statements here. This is similar to our hash join, depending on the index usage, where your order M plus N. Okay, not great. Now here's a common one. Now I've just shown a left outer join here. You could put any other join. You could do an inner join or whatever. And this is where the problem truly comes in. Because I have to search through all of my users and all of my IDs in the user and post tables there. And this is probably the worst case scenario, and yet it's one of the most common things that we do as data scientists. And this is order M times N. That's horrible. That means this is a really, really slow query. And like I said at the beginning, when we are thinking about whether I have a graphy problem, I said one of the hints was if you have multiple joins. So think about this. If I'm joining this table, the results from this query to the results of another query, maybe I've got multiple tables and I'm having to join across, multiple columns. This gets really, big O gets really ugly for us really fast. Okay, that's one of those things that we want to try to minimize in life. And then let's not forget how complicated SQL queries can get. I don't know about you, but if I need to search for something on SQL online, there's just some really bad information out there. It's really difficult to read. As a student in particular, or as somebody who's, maybe you're not a data scientist, but you work with them, it's really difficult to kind of piece together what's happening in some of these queries. So I really feel for people as they're learning SQL and, they go into these like Stack Overflow questions and stuff like that, because they can be really complicated. So let's talk about what graph databases can do for you here. Now, the first one obviously is going to be faster queries. SQL, if you're searching for relationships, which we're going to do today, relationships between data points, SQL has to search over an index. It has to look up over that index, and that's slow, as we just talked about. Whereas graph databases treat relationships, we say this a lot, they treat relationships as, first order entities, first class entities. And what that means is that because our data is stored as relationships within a graph database, searching across them is super easy, it's super fast, it's super efficient. We'll also see today that it allows for more intuitive queries. If you have a graphy problem, if you have a problem that lends itself well to a graph structure, the queries are really quite elegant. So, we might think about that thing that I said earlier about why should I learn a whole new query language? Well, the answer is going to be because it's simple. It really, it makes life a lot easier. And it's very easy for, somebody who might be reviewing your code. It's really easy for them to quickly understand what your code is doing. And then, like I said, the queries are designed to take advantage of the relationships within the data. This is, that statement about treating relationships as first-class citizens. Okay, now we're going to play a game. How to identify a graphy problem. And I said before, when relationships between the data points matter, but they might be subtle. Okay, we might not always realize that we have relationships. Now, here's an example. This is off Kaggle, and I probably the students in the room are more familiar with Kaggle, or I shouldn't say that, but a lot of people in this workshop are probably familiar with Kaggle. For those of you who aren't, it's an online source of data science competitions, data sets, notebooks of examples, just a really great resource. And this is just one example looking at churn. Now, this is an eye chart, so I don't expect that you can read the data and all the columns here. But basically, they're looking at customer churn from a bank. Okay, so I've got different customer IDs, their credit scores, where they live, their gender, their age, etc. So the idea with this data set is you're going to create a machine learning model. And I saw somebody had some statements earlier that they were working on, I think Milan, working on machine learning problems and looking to maybe extend that ML to the graph space. We're so going there today. Okay, so the idea here is I want to create an ML model to predict the probability of a given user churning, and you can do that. We've got feature vectors here. We can do some feature engineering and turn those into embeddings. And we use those embeddings as the training, the input for our models. And that's cool. Now let's take a step back here. This is a bank. Okay, and I've got different customers within this bank. Let's say my spouse decides to leave the bank, decides to close accounts and move to a different bank. Okay, well, I'm probably going to do the same thing because we have joint accounts. So what that says is that there's actually a relationship between customers within this particular columnar data. And we can't ignore that. We get better models, and I'll show you an example here in a minute. We get better models when we consider the relationships among the data. Okay, so in just columnar data, you can't do that. So the rule of thumb that I like to use is if you have more than a couple SQL joins, now that wasn't true in that previous problem, but if you have more than a couple SQL joins, then you should suspect that you have a graphy problem. Now, I'm not going to sit here and tell you that the graphy solution is always the best one, but definitely give it a try. I'll show you a case where it is here in a minute. But now we're going to play a game. Okay, so the game that we're going to play is Will It Graph. Maybe you're familiar with Will It Blend, and there was this blender, if you're not familiar with it, that they would throw all kinds of things into and find out if the blender would actually blend the thing. So this individual here is looking to blend an iPad, and spoiler alert, yes, the iPad did blend and wound up as powder within this blender. But we're going to play Will It Graph. And what I'm showing here, this is a pretty classical machine learning problem in image analysis called MNIST. And a lot of people start learning about analyzing images using MNIST. And so the question is, will MNIST graph? I'm going to give you a second to think about that while I grab a sip of water. Okay. So thinking about this data, I truly, if you think about this, I have columnar data here. I have my pixels, which have, by pixel index, I have two-dimensional indexing. You can think of it as like a NumPy array, some sort of array representation of data. However, I don't have random noise here. I have a digit. And so neighboring pixels have relationships with each other. And so, yes, we can represent that as a graph. You would assume that there's some sort of continuity from one pixel to the next. You're not assuming I just don't have random Gaussian or Poissonian noise. One pixel is going to have some sort of smooth relationship to the next pixel. So yeah, images are graphs. Okay, will it graph? Facial recognition. Give you a second on that one. Probably you already know the answer. And probably you're going to figure out the pattern here. Will it graph facial recognition? Absolutely. When we talk about faces, there are relationships between the points of the face. For instance, the bridge of the nose. I don't have some sort of jagged bridge to my nose. There's a smooth path there. Same like with the outline of the lips or the eyes or the eyebrows or something like that. So we definitely do have relationships among those points on the face. Okay, this one is obvious, drug discovery, right? When we're talking about drug discovery, we're talking about molecules like what's on the left here, and you know, certain elements bond with other elements. So, hydrogen and oxygen bond with carbon really easily, or nitrogen really easily. And so we can describe molecules as graphs. Um, where the elements are just the nodes and the relationships are the bonds between them. No workshop would be complete in this day and age without um, some sort of reference to COVID. And this is kind of a pretty popular graph, looking at peer-reviewed journal articles and the common terms between them. And so what we see here, our nodes are colored based on community detection. And what we see, in the center, our size is how many times that particular term appears within this corpus of data. So you can see coronavirus infection, pandemic, things like this. They're very popular terms, and they're larger. Terms that occur less frequently are, these are smaller nodes. So for instance, if you look at the large blue node, let me see if I can turn on my laser pointer here. Okay, there's this large blue node down here that's called SARS, makes sense. And it's in the blue cluster, it's the one that's used most. Now, let's look up at the yellow cluster here. I have female and male, I have middle-aged. So what I can see is that this yellow cluster up here has been identified as being similar terms, and these are describing the characteristics of people. Okay, so that makes sense. So yeah, definitely we can talk about coronavirus in a graph context. Now, this is a fun one, natural language processing. Now, y'all have probably figured out that all of my will it graph examples, of which this is the last one, the answer is yes. But how? How is natural language processing a graph problem? Well, I'm glad you asked. Okay, this is pretty small here, and the point isn't that you can read it. The point is to understand the relationships here. What I've taken is part of the first sentence of Barack Obama's Wikipedia entry, and there are relationships between words. For instance, here's the word is. Okay, and is the root of the sentence. If you work in NLP, that's great. For those of you who aren't familiar with the root, it's the most important verb within the sentence. It describes what's happening. But there are words that are important to the word is. For instance, I've got this segment up here where I have the words Barack Hussein Obama II. And these are called compounds, but they all have a relationship to the word is. Okay, it might be hard to see, but the arrows kind of go in this direction. Here, the Roman numeral 2 relates to the word Obama, and it also relates to the word Hussein. This was created with Spacey. For those of you who are interested in NLP, it's a free Python package for doing some really nice NLP, and it'll create these figures for you. But there are relationships between words, and so we can graph those relationships. And it's actually, I believe, the basis for a lot of NLP algorithms out there is understanding which words connect to which other words, because we know it happens in certain predefined patterns. Okay, cool. All right, let me just grab a quick swig of water. All right. Why can graphs be better than tables for graphy problems? We've kind of been working up to this, but again, it comes back to that question. My data is already in SQL. Why should I bother? I can do this in SQL, and I'm going to take you back to this one, our Kaggle thing. Traditional machine learning, if you get right down to the math of it, assumes that all data points are independent from all other data points. It's the basis of the math behind like every ML algorithm. And we already talked about how that is not necessarily true in a data set like this one, that the relationships between these customers matter. And so if you put this data into your machine learning model, and we don't know in this data set, by the way, if there are spouses in here or friends in here, maybe friends moved to other banks. We don't have that relationship information. I'm just kind of calling this out as an example. We're going to use another data set when I do the demonstration on this. But we don't, we get a better model when we treat our graph data as an actual graph. Okay, let's talk a little bit about that. For instance, machine learning. One of the things that we have to do in machine learning with natural language, when we're trying to do machine learning on text, which we would do in a natural language processing or NLP problem, we have to convert text to words. Okay, we're going to have to do that with a graph too, and I'll show you how we do that in a bit. But this is one approach. This is called word to vec. And what we're doing here, it's the skipgram approach. I'm not going to get into the math behind it. Those of you who are interested in NLP, there's all kinds of resources out there about it. But let's say that I start with document X, which is this orange text, and it says, gave a research talk in Boston. Okay. What I do is I go through that sentence, and we basically are saying, okay, gave research, and we're skipping that word um, and we're going through and we're creating this mathematical model of what words are appearing next to what other words. Now that's a hint for you: words appearing next to other words, or two hops from those other words. Okay, so then we get this whole vector. Or embedding that took that text and it turned it into a list of floats for us. Now, I have another document over here in blue, had a science lecture in Seattle. Now, when I have vectors, what I can do is project them in an n-dimensional space. Here we're showing a two-dimensional space, and try and determine things like word similarity that could represent distance between two vectors. It could represent the cosine similarity of them. So what I see here is like the word Boston and the word Seattle are pretty close to each other within this plot here. Talk and lecture are close to each other, but lecture and science are not. So talk and research are not. Talk and Boston are not, because they're not similar words. So we're calculating word similarity here. And we can do the same thing with graphs. Okay, in order to do that, we have to create, what we call a graph embedding. And there are many ways to do this, but and they're similar to NLP, but the problem is that when we did NLP, we assumed this linear movement through the sentence. We go from this word to this word to this word. Well, that doesn't have a lot of meaning in a graph. How do we hop around a graph? There's no, like one directional thing that we can do like we can with words. Well, the answer is that, in very broad brush strokes, when we create embeddings for graphs, we tend to skip around the graph in some sort of random way. We can go from node to node to node. We can do that several times, and we can do that with weighted graphs. There's a whole bunch of different ways to do it. They tend to fall into two categories: transductive and inductive. And when you're talking about these transductive embedding techniques, are one where you create your embeddings for the whole graph. You do it once, but if you add a new node in, then you have to retrain your embeddings. So that has the benefit of being fast. You do it once. You don't worry about new nodes coming in. But what happens if you have a dynamic graph? Well, then you go to an inductive model, and inductive models can take advantage of those new nodes coming into the graph and calculate their embeddings as it happens. So you don't have to retrain the entire graph. But the downside, there's no free lunch here. So the downside is that inductive algorithms tend to be slow. We can talk about matrix factorization. All graphs can be represented as a matrix. It's the basis of a lot of math. And this is the adjacency matrix. So it's a matrix of which nodes are connected to which other nodes. So you can do different factorization on that. We can have random walks, like I said. We're going to talk a little bit about the graph data science library that is part of Neo4j. And there are a couple methods in there for creating embeddings. One is called FastRP. The other one is called Node2Vec. Node2Vec is kind of similar to that Word2Vec approach. FastRP is a little bit more random about the graph. It's actually, as the name suggests, is pretty fast. RP stands for random projection, in case you're curious. And then there are other methods based on neural networks. They start getting pretty complicated. That's going to be beyond the scope of today. Okay, but what kind of things can we do when we have graph embeddings? Well, the answer is all of the machine learning that you do just in classical machine learning, you can also do with graph embeddings. I mean, all I'm going to get out of this is a list of floats. It doesn't matter how I got that list of floats. It's just a list of floats. I can put it in any machine learning model I want. So like we could do something like node similarity. Like we did word similarity, here we could apply anything, looking at vectors. We could do Jacquard similarity, looking at which nodes are in common with which other nodes, cosine similarity, Euclidean distance. We can do k-nearest neighbors. So these are just all, standard machine learning terms. It's just that the data that we're giving them happens to be graph embeddings. So like I said, all of the same ML models, classification, we can do binary classification, we can do multi-class, multi-label classification, we can do regression, clustering, dimensionality reduction, similarity. All of these we are familiar with from the machine learning world, like the traditional machine learning world, same stuff. You could throw these embeddings into the same packages like scikit-learn, TensorFlow, Keras, PyTorch. You can use them all there. It's just they happen to come from a graph. But the cool thing is that in addition to the traditional approaches, there are also things that we can do with graph data that you can't do with traditional machine learning, such as link prediction. An example of link prediction would come out of social media. So I have a network of relationships. This person is friended with that person in a Facebook kind of model. They're both friended with each other. This person follows that person on Twitter. But let's say I want to recommend somebody to, hey, you should friend Bill. Okay, well, what's the probability that there truly is a link between Bill and I just haven't friended him yet? Okay, so that's link prediction, and you really couldn't solve that problem very easily in traditional machine learning. And then subgraph level structural similarity. For instance, let's think about drug discovery. We're looking for molecules, and maybe this molecule over here has this chunk over here that's a little similar to this other molecule over here, and we might expect that chunk to treat something well in this disease, and therefore maybe it also applies to that disease. Okay, you totally can't do that I'm aware of in traditional machine learning. But if you want to prove me wrong, I am totally all ears for that. I love being proved wrong on this stuff. So reach out to me if you have a counterexample. Okay, let me show you actually doing this on a real data set. So what I have here, it's the Cora data set. And the Cora data set is looking at scientific publications. And specifically, there's roughly 2,700 of them. And it is there are 7 classes. So this is a multi-class problem. And it's hugely imbalanced, just so you know. The classes are, they're like machine learning classes. We'll go through them in a minute here. And what they're looking at is which papers are citing which other papers in these academic journal articles. And so that's an obvious relationship there. Now, one of the other bits of information that they've provided about this is they've created NLP vectors via one-hot encoding. For those of you unfamiliar with one-hot encoding, basically what you have is you have a vocabulary of words, and each element within like here we have 1,433 words. So I have a vector that is 1,433 dimensional associated with each paper. And so each element within that list corresponds to a word. Okay, so maybe the word machine, and then the next one would be the word learning. And so you get 1 or 0 depending on whether that word appeared within the abstract. So somebody has gone through and created a vocabulary. They decided what the most important 1,433 words were. and they won hot and coded. So they created the vectors for these. Now, this is a publicly available data set. It's kind of, a pretty traditional graph data set, like MNIST is traditional to image analysis. But I don't have access to the vocabulary. I don't have access to the abstracts. I don't have the ability to go in and create my own word vectors. So, let's just keep that in mind, that these vectors are just what they are. So then I have a graph model here. And what my graph model is just one paper, that's my node, is citing, that's my relationship, another paper. And those nodes have some properties. They have an ID, they have their subject. So this is a supervised machine learning problem. We don't have to do supervised within graphs, just like traditional machine learning. But in this case, we're lucky enough to be working with a supervised problem. So that subject is what the paper has been labeled as. And then we have features, and that's those word encodings. So let's look at it. I looked at this data set in two different ways. I created two different models. Now, my goal was just to compare the quality of the embeddings. So I wanted to keep the machine learning models identical. All I'm doing is throwing in different embeddings, okay, word embeddings or graph embeddings. And then I wanted to keep the machine learning model simple. So I used scikit-learn. I used a support vector classifier in there. I went with all of its default settings. I didn't optimize any portion of the support vector classifier beyond those default settings. Sorry, that's my pair programmer in the background. Her name is Bella, and sometimes she gets a little vocal. So, and again, this is the caveat that I did not have access to the word vectors or the vocabularies for tuning. You'll see in a minute that I did tune the graph vectors to make a point. So both models were given the same task, multi-class classification with an imbalanced data set. Some of these data points, it was like an order of magnitude less than the ones that had the most data points of that class. Okay, so let's look at what we got. Okay, using the word vectors. So, this is that just the pre-provided vectors. What I got, as you can see here, I got a mean accuracy of about 73%, which, that's not bad. It's better than a chimp flipping a coin. And by the way, I want to point out, I wrote a blog post on this, so you can see this in a lot more detail. And this is where you can find it. It appears in Towards Data Science on Medium. You can see our confusion matrix, and, it's okay. But in some cases, my true label versus my predicted label, look at this. I'm like, 54%. So I'm not really good with that particular class, like almost a chimp flipping a coin, right? Some of them I do better, like here's 79%. And if it turns out, if you actually look at the data set, this class 0, I'll show you what that is in a minute, has the most instances within the data set, and class 4 has the least. So these results are not surprising. But let's look at what happened when I did this with graph embeddings. Now, I created, in this case, remember the word embeddings, I had a 1433 dimensional vector for each paper. I'm only going to, I believe I used a 256 dimensional embedding for each paper. So automatically I have a smaller data set. I'm using up less memory, just out of, I just randomly picked 256. And when I did so, I got a mean accuracy of 85%. So I've increased by like 13% here just by going with a graph. I have smaller dimensional vectors and I got better accuracy. And if I look across to my diagonal here on the confusion matrix, you can see that like the lowest one I have, which was again that smaller class, that lowest one is still 76%. So I'm even performing better than the word vector model, the 73%, on my worst class. Well, that's pretty cool. Okay, let's look at like the actual vectors. I've done a two-dimensional, this was TSNE, the T-distributed stochastic network. Yeah, sorry, don't have that one memorized. But it's a dimensionality reduction. So I took those 256 dimensional vectors and I boiled them down to 2 dimensions, which you can kind of see some clustering happening in here. It's pretty hard to go from 256 to 2, but these are those network classes that I was talking before. So neural networks, that is 0. That was class 0, and it has the most number of papers in here. And in my plot here, my TSNE plot, that's this red cluster here. So it kind of does cluster. Um, let's see, I have theory. That was the one that had the lowest number of instances, 4. And 4 is kind of this blue color, which is this cluster down here. So you can see it really is clustering. Let's see, what is this purple one here? Class 5. Class 5 is genetic algorithms. What's this green one? This is class 2, reinforcement learning. Okay, so you can see these are not always a lot of data points in here, but I am getting clustering based on the graph embeddings. So that's cool. That's a good gives you a good vibe that maybe we're going in the right direction here. Now, I did decide I wanted to tune my hyperparameters, so I used the Python package uptuna to do so. For those of you who like to compete on Kaggle, most of the winning models do hyperparameter tuning, and a lot of them use uptuna. So what I did here was I looked at, I varied a few of the parameters using uptuna. And when I did that, I got my mean accuracy up to close to 87%. Okay, so that's 87% versus 13%, or I'm sorry, 73% on my word vectors. Obviously, I have achieved goodness here by going to a graph model. And here I can just look at which hyperparameters mattered the most. I was using the FastRP algorithm to generate my embeddings. And I can see that the dominant hyperparameter here was embedding dimension. Now, different data sets are going to give you different results. So don't take this as being, the gospel that it's always graph or the embedding dimension that matters the most. These are some mathematical hyperparameters associated with FastRP normalization strength. Again, go look at this blog post because I go into this in a lot more detail there. Okay, how are we doing on time here? Excellent. Okay, what I want to do, we're going to do some live coding here. And specifically, here's what we're going to look at. That's a reminder, by the way, of the repository. I'll put it back up here on the screen in a minute. We're going to have a graph model, and we're going to look at airports and routing between them. So what I have here is I have my nodes. Again, there's my pair programmer. She doesn't write very good code. The PRs, I have to spend a lot of time reviewing them. Anyway, so I have my airport nodes, and airports are on continents. That's a relationship here. They're in cities. They're in regions, and those are just kind of like geographic regions within a country. So my region might be in country. So this is the model that we're going to use. There's some tools that if you want to live code with me, you're welcome to use. You're welcome to just sit back and watch too. Don't feel like you, have to participate. This is the link to the repository. There's a few things in here. We'll go through it in a minute. But we're going to take a break in just a second here so everybody gets an opportunity to clone the repository if they want to code along. We're also going to be using some free sandbox instances, and I'll show you how to get there and set those up in a minute. We will be using some Python notebooks. You have a choice of using Jupyter notebooks or Google Colab. I'm going to use Colab today. You can use VS Code notebooks, whatever you're comfortable with. So that's my notebook environment, but you will need to install the official Neo4j Python driver, and it's just pip installable, so that's cool. And then we're also going to be doing SQL. We're going to be starting with SQL, and if you have SQL already installed on your machine, that's cool. You don't have to install this, but there's a Docker container within the repo which will install the data or install Postgres, which is what we're going to use today, and pre-populate the databases for you. So if you want to go that route, cool. And if you want to use your own, that's cool too. There's going to be one query that we do that's rather extensive, and I have written it for Postgres. It may or may not run for you. So there's some looping that happens in there, and all the SQL variants handle that a little differently. Okay, so we're going to take a break here. We're going to take about 10 minutes. So that'll give you a chance to clone the repository. And it's also going to give me a chance to answer questions. So if you have questions, please type them into chat. I have 51 minutes after the hour. So let's try to come back right on the hour. If you need a bio break, cool. And I'm going to stop. Okay, everybody write down this repo. We'll put it in chat if you don't have it, just ask if it's not already as a sticky in there. And we'll be back at the top of the hour. Okay, stop share. All right, cool.
Cool. Yeah, we could have left it on screen, but this works also. So people can. But I have put everything in chat. So if people should have the link to the repo, have a link to the sandbox. So I guess that gives us some time to go into questions. If somebody needs anything, right? Type it in chat. Let us know what you're missing, and then I can dig it up for you. All right, questions. One question that came up was, what's the best hands-on training to build query and model graphs, and how are they? Yeah, how to start basically.
Yeah, that's a great question. There is a thing for education on Neo4j. It's called Graph Academy, and Graph Academy has just tons of content in there, starting with absolutely basic Cipher, going all the way through some very sophisticated queries. And there's videos there. The other place that I would recommend going, which is someplace that we are going to go in our live coding portion, is Sandbox. So what Sandbox gives you is a bunch of pre-populated databases, and several of them have these things that we call browser guides, which will walk you through different things that you can do with that database. There is some very basic ones. There's what we call the movies database. That's a great starting point for learning Cipher. But then we also have a graph data science pre-populated database. And right now, it's got a Game of Thrones graph populated in it. We're going to be releasing a new GDS sandbox here imminently. GDS 2.0 is coming out basically tomorrow. It's going GA tomorrow, and there's some syntax changes from what we're doing today. I'll try and point those out as we go through the code. But the new sandbox will walk through that, and it actually uses the graph that we're using today.
Super. Mohamed asks, which sandbox project should we choose for the training now?
If we're going to set up Sandbox, I'm going to assume the question is we're going to set up Sandbox today.
Yeah.
We'll be using a blank one, and I'm going to show everybody how to set that up in real time. That's going to be part of our workshop.
Okay, so basically just register for it, be able to access Sandbox, and then wait for Claire to guide you through. Okay. Robert asks, is the MNIST image problems efficient useful when expressed as a graph?
Never having, I'll just be upfront and honest, never having done it before, I couldn't tell you. But if you do it, I would love to hear about it. So that'd be a great thing to talk to us about in Discord.
Yeah. Let's give it a go.
Yeah, that would be fun.
Yeah. Yeah, there was a question about earlier when you presented the Willet graph, and then you had M and N as variables. What does M and N mean? I think you mentioned it, but maybe quickly repeat what it was.
I think that was in the discussion of the complexity of different SQL queries.
Yeah.
So what those were the table sizes of each of the tables we were joining on. So like if I had two tables, one of them would have N rows and the other one would have M rows.
Cool. And then, I mean, I don't know if, I mean, we will go into that a little bit, I guess, but we can maybe as a short teaser or setting the scene rather for what we're going to do is what's or where does Neo4j differ most from SQL and from SQL Graph database, because there is also a thing like SQL Graph.
Right, right. So that's a great question. Where it differs most, let's take the first half first. Where it differs most from SQL is how the data gets stored. So with SQL, you have an index, and that index points to a row, and that row has columns within it. So in order to search for relationships within that data, you have to do some fancy joins here, which we're going to do in a minute. In the live coding portion. But then when you have a graph database, it's the data is being stored by relationships. So because the relationships are what matters here, think of them, kind of like an index. It's not quite an exact parallel, but you're searching across relationships. So that data is already set up for you with that as your primary key, if you will.
Then there was from Badri just now, the pushback I get from SQL purists is that they can make joins efficiently by adding appropriate indexes. Do you have an example where graphs are more efficient than an optimally indexed SQL?
Yes, and we're going to do one in a minute.
Cool. So stay
It's going
tuned.
to be fun.
Yeah.
I'm never sarcastic either. Sorry, I'm getting a lot of the video is washed out. I have my curtains down, but there's a lot of sun out today, and it's reflecting off the snow. So I'm, super washed out right now.
Not a problem. Yeah, the question is maybe a bit more complicated, and I try to summarize it here. They have various images, and I try to determine if they're actually the same piece of what's on it. He says toast. So let's say if two images of a toast, if it's the same toast, or if it's just a flipped toast or slightly rotated.
Ooh.
Your talk suggests converting images to graphs might be a solution. Is there some way to do that, or is there some kind of algorithms where this could be graph algorithms could be helpful in such a detection of similarity?
So never having done it, here's how I would think to do it. When you have an image, actually, no, I have done it, but I've done it all in imagery. And what I did, if you go to my GitHub page, there's my main profile, and there will be a link on there. And it's talking about graphs of code. It's one of the very bottoms of the link. And what I did was, if you're unfamiliar with how compilers work, they use these things called abstract syntax trees. Which basically say this bit of code is linked to that bit of code. Code, like meaning software somebody's written. And I was trying to find, this is back when I worked at GitHub prior to Neo4j, we were trying to use machine learning to find identical blocks of code, function to function, even among different languages. And so I took the data, the ASTs, and I represented it as a graph. And by representing it as a graph, what I mean is that I used the adjacency matrix. So I said which bits of code are connected to which other bits of code based on the abstract syntax tree. There's a video for this on my GitHub, so you can go learn more about it. But, basically the spoiler alert is I represented code as an image. So it's kind of the reverse problem that we're talking about here. But the adjacency matrix looks like an image. It's just ones and zeros. And then I used TensorFlow to basically do similarity. And what we found we could do was we could get a really way above 90% accuracy, even if it was across multiple languages. Like, let's say, Alex, you wrote a function that calculates cosine in Go, and I wrote it in Java. We could even identify that those were similar blocks in two totally different languages based on the abstract syntax tree, which is language agnostic. Now, if I were to do this starting with an image and going to a graph, so that's the opposite problem, I would still look at using the adjacency matrix. And can I treat my image, so like those MNIST images, those are just pixels, rows and columns of pixels, and that can set up your graph for you. That's probably how I would start doing it. Again, super interesting. And if you make it work, please come onto Discord and show us how you did it. Because I apologize, I don't have the link for that MNIST thing in my slides, and now I can't find it anymore. So let us know how you do it. It would be a super fun problem to do. And for those of you who are students in the room, or you might be looking for a job within data science, that was one of the other questions on our survey. This would make a really fun thing to have on your portfolio.
Yeah. Should we do one more question, or do we
Yeah, let's do it.
dive back in? Okay. Tyler asks, is Neo4j recommended mainly for exploration, processing, and analytics, as opposed to general storage?
Oh, interesting. Yeah, the answer is both. Both and. We're going to be talking about analytics and processing, but you can store your data there. But as a data scientist, I would say, well, why just store the data? What's the purpose of storing data if you're not going to do anything with it? So everything that I do is all analytics and data science. And one of the nice things is that there's tooling that exists within Neo4j, namely GDS, Graph Data Science, that will allow you to do some very sophisticated things. And we're going to do those today.
Okay, cool. I guess towards the end we have a bit more time, and then we can go into questions again. But let's maybe continue now with the session.
Okay, I'm going to turn off my camera again and start sharing screen. Let's see. Okay, we're going to go into infinite zoom here for a sec. Okay, Alex, if you can tell me when you're seeing my slides again.
Now we lost your slides again.
You lost my slides.
Yeah. Huh. I think you just clicked on stop sharing instead of hide on the button. Maybe you can.
Silly me. Okay, let's try this
it's
again.
Back.
It's back. You see him?
Yes.
Excellent.
Perfect.
Okay. So for those of you who are looking to code along, hopefully by now you've cloned the repository. We'll worry about Sandbox here in a minute. Let's just quickly go through the repository. So this is it here. And we're going to be using most of what's in here today. You will notice that here's the SQL directory, and there's two subdirectories here for database population. We're not, if you want to run this on your own instance of SQL, you can look at these things here. This is basically just traditional SQL. The data files are in the repo. Okay, so let me show you. It's in the folder cleverly named data, and they're just CSV files. Okay, and then also in the SQL directory, we're going to run some queries today, and these are the queries that we're going to run. So you can basically just copy and paste these things. We will also be using Cypher today. Cypher is the query language that is used in Neo4j, and it takes a little getting used to, but I think you're going to find today it's not that bad. Okay, and specifically, just how we're going to populate the database. In my view, one of the trickiest things in Cypher is just populating the database. And there's a few different ways to do it. We're going to use this thing called load CSV. It's not always the most efficient way, but this is a pretty small graph we're going to be working with. So for today, it's going to be fine. And then we have some notebooks here, some Jupyter notebooks. Like I said, I'm going to use Google Colab for these, so we'll worry about those in a minute. But I want to really draw your attention to this Docker Compose file. And what I'm going to do, and Alex, if you can let me know if you're seeing my VS Code screen.
Yes, screen is visible.
Excellent.
Yep.
Okay, so what I've done here is I've created just a Docker file, a container for us today, and it's got a few things in it. First off, it's got this Portainer. We'll show you what that looks like in a minute. If you've not used Portainer before, I was recently introduced to it, and I love it. It's just a really nice way for seeing what's going on in your containers and managing your containers. So I've got that set up in there. You don't have to use it if you don't want to. I have Postgres in here. So, this is just going to create us our database. And then I have a bunch of SQL files in here in the database population subfolder. And so what this is going to do is we don't have to spend our time creating our actual tables. This is going to just do it for us, saves us a little bit. You can see I have my usernames and passwords here. They're wonderfully sophisticated. And then lastly, I have PG admin in here. You don't have to use this. You could do all command line queries. That's fine. I've just put these in here, in case you're interested, but whatever you want to use is cool. And so what we're going to do, let me make this maybe not quite that big, just a little bigger. Okay. All we have to do is we're going to issue this command, docker compose build. Okay, and it's going to just tell you as an image. And then I'm going to use docker compose up. Okay, so it's building my containers now. I've already populated the database, but if you haven't populated it yet, it's going to give you a whole bunch of messages from your Postgres container saying it's bringing in all of the data. Okay, so cool. So let's see what we've got running here. I'm going to go into Portainer. And Portainer exists on port localhost 9443. So localhost colon 9443. When you first do this, it's going to ask you to create a password. It'll actually tell you that, oh no, this is not a secure site, and you need to click the advanced button and tell it, yes, really go to this localhost thing. And it'll ask you to set up a password. I've already set one up here, so I'm just going to log in. Okay, so let's log in here. And this is what I get. This is what it looks like. Okay, and so I can see here I've got 4 containers running. I'm just going to click on this 4 containers thing. And I apologize, I'm going pretty fast. There's a lot to cover in the live coding section, but again, the videos will be made available if you want to go back and refresh on this. So I've got my dashboard here. I'm going to click on my 4 containers and you can see what I have running. Ignore Neo4j. I've just got some container off running on its own. So we're not going to actually use that. You don't actually have it in your Docker container. So PG container, that's my Postgres container. I've got Portainer. Get rid of this. Okay. And then I've got my PG admin. So what I can do, any of these things I can click on. Okay, so I can click on here and I get just connect this way and I get a terminal window. Okay, so I can, and this command is in the README that if you're not familiar with running, we're going to use pSQL. So if you were to go into the README, what I can do is I can issue this command. My user is Postgres. Okay, and so I can list my databases. And what happened here was we created this air routes database. So I'm going to change to air routes. Okay, and now I use \DT to see the tables that are here. And so these tables are what were populated by those database population queries. And I'm just going to go select star. Yeah. I'll go to touch so we can actually see this. Select star from airports. Let's go limit 5. Okay, so we can see that we have data here. I'm going to work mostly with PG admin just because it's going to make for some easier demonstrations. So let me just disconnect with Control D from there. And that's I'm going to log out by clicking this disconnect button up here. Okay. All I'm wanting to show there is just that we have populated databases, populated tables, but I'm going to go into PG admin for container. Okay. And in order to do that, this is running on port 80. Okay. So I'm just going to click on this published port 80 thing. Okay. And here is PG admin. Now, if you look at, let me just show you really quick. When you're looking at the Docker compose file, the YAML, your passwords are all in here. So for instance, if I was looking at the just the Postgres container, my user is Postgres and my password is let me in. Now for the PG admin container, this is my login. They want an email address. So I just made one up and I have let me in. It's going to give me some nasty messages about that. So you'll see them in a minute. So I've got my login as admin@admin.com. My password is let me in. Okay, this is not the world's greatest password. It's going to give me errors saying, oh, that's compromised, blah, 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 blah. I don't want to save it. I'm using an old version. Okay, fine. Okay, we need to tell PG admin to connect to our the Postgres container. Okay, so to do that, I'm going to click on Add New Server. And again, I apologize that we're going so fast. Here's the thing, is that my PG container is running on a certain IP address, which is right here. These are just local addresses, and it's going to want that here. So I want to copy that. Okay, and I'm just going to call this server connection PG. Then I click on connection here, this connection tab, and I need to give it the host address. So that's IP address. Now, again, here in the repo, you see that my Postgres user is Postgres and my password is let me in. So I need to tell that to PG admin. So my username is Postgres. My password is let me in. I'm going to save it just because. Okay, so now we've connected and I can see my databases and air routes here. It'll connect in a second. Okay, cool. Now I'm going to go into tools. Okay, and I'm going to hit query tool right there. Okay, so this just gives me a nice little editor for doing some queries. Now I'm going to start running some code, some SQL queries, and I'm using in the repository, there's the SQL directory, and then there's something called workshop queries. Okay, so I'm just going to be copying and pasting lines out of there if you want to follow along. First thing I'm going to do is I'm just going to check my databases are all cool. So in DB population checks, that's where I am right now in the repository. Okay, so I'm just going to count my number of airports here. Okay, and then if I want to run this, I can click this little run button up here, or I can just hit F5 and it runs. Okay, so I have 3,500 airports. Okay, let's find out how many countries I have. You can go through all these. I'm not going to do all of them right now. Okay, so I just listed the countries. I didn't count them, but you can see that there's a country code and then there's a description. These country codes are kind of standard across the internet, so you can scroll through those and if you feel like it. One thing I want to point out, there's a table called routes and a table called iRoutes. So I'm going to look at iRoutes here. This is the very last line of that database population checks.sql file. Okay, now what I have here, I've made some relationships. I have a source airport and I have a destination airport, and these are based on airport codes. And the airport codes are provided as properties within our the airports table. Okay, and then I have a distance between my airports, which is cool. Okay, so that's what's in our SQL here. You know what? Let me blow this up just to be safe. Make that go away. Okay, now let's start running some actual queries. So what I want to run first, there's a query called indegree.sql. Now, what indegree is it tells you how many nodes have a relationship coming into my target. Okay, so what this would indicate for our airports is how many flights arrive at my airport on any given day. Okay, this is a pretty simple, straightforward query. Okay, let me show you what it is. Okay, can I minimize that down? Yeah, cool. Okay, so here I'm selecting the destination in my iRoutes table. Okay, so remember that's this table that I was showing down here. Okay, you go away. And I'm grouping by my destination. Now I'm counting the number of things that are coming into my destination. I'm counting that as in degree. And I'm going to order this based on descending in degree. Okay, so let me give that a run. Of course it is. Let's see, what did we do wrong? That's very strange. Okay, so the beauties of live coding. I'm demonstrating here the difficulties sometimes of debugging SQL. That's odd. I just reran it and it ran fine. Okay, maybe that's going to show you one of my loves of SQL is that why did that just happen? I didn't change a thing and it ran. So again, live coding, isn't it great? So I can see some in degree results here. So for instance, IST is Istanbul, and it's got 307 flights arriving into it, as does Frankfurt here. This data set is publicly available. I believe there's a link to it in the repository README. It's not exactly the most current data set, so don't over index on, wait a second, what do you mean Istanbul has the most and Frankfurt has the most flights coming in? That's just what happened in the data set, what happened to be back when this data set was created. Okay, now that's all well and good. That's our in degree query. But let's now look at complete degree or total degree. So I'm looking at complete_degree.sql in our repository. And I'm just copying and pasting it here. Okay, now this is getting a bit longer of query here. If you follow me on GitHub or anything like that, you'll know that I use common table expressions with reckless abandon, which is what I have going here. If you are if you're somebody who's like a student or you're doing a lot of joins, these can save you time. They can cut down on how much time because it's not going to do everything until the very end. So basically, I'm getting complete degree is looking at not only the number of flights coming in, but it's adding it up with the number of flights going out. So it's looking at the total number of relationships associated with my airports here. Okay, so here is, I'm first getting my out degree. So this is very similar to in degree, except I'm selecting sources from my iRoutes table. And I'm grouping it by source, and then I'm getting my in degree just as I did in our last query. Then what I am doing, I have an inner join right here. You see it? Okay, so my inner join, as you remember, is expensive. That's order M times N. Now that table, remember, we're basically joining on the same of the sources from that iRoutes table, and I have my targets, my destinations from that en route table. That en route table is the number of relationships. I haven't counted those, but I happen to remember off the top of my head, it's about 73,000 air routes. No, that's not true. It's about 45,000 routes among airports. So my order, my big O on this is order N times N, since it's the same tables. So, that's 45,000 times 45,000. Okay, those are small tables, but just keep in mind, like if you're working with larger tables, what happens when those are, 500 million rows? That's not going to be fun. It's not going to be fast. Okay, and that's only one join. Okay, we're only doing one join here. Think about what happens when this becomes lots of joins, as you're going to see in an example here in a minute. Okay, so basically I'm adding my out degree and my in degree on this join. Okay, so we're going to give that a run. And of course it does that. Okay, I just kept running it. Don't ask me why that worked.
Sam in chat says it's might be because you have a line highlighted and then it executes on that line.
Could be. Yeah. Yes, I'm sure if I ran this in the command line, it would It would 100% agree with me. So I'll try that on the next time we run something in here, Sam. Thank you. Okay, so I can see that Frankfurt and Istanbul also have, a large number here. You can scroll through this list on your own and find your favorite airport. So my query is a little bit more complicated, right? Now let's get a little bit more complicated. Okay, so let me delete all that. Okay. I am going to run a query that's called exactly underscore 2 underscore degrees. Now, what this is asking for is I want to know if I have a starting airport, how many airports can I get to in exactly 2 hops? So let's say I feel like riding an airplane twice in a day. My starting airport is Denver, who has an airport code of DEN. So I'm going to run this for Denver. Okay. Was that the correct? No, it didn't. I didn't copy it apparently. Okay. All right, so let's go through this here. This is to get exactly 2 hops. So my target airport is I'm going to get Denver. So I'm going to get all of the routes from Denver. Okay. Now I have this second query. So I have this as a common table expression, a CTE right here. So all of the routes from Denver are basically coming up as their own little temporary table, not truly a temporary table in SQL language. But then I'm going to get all of the destinations for every city within that table. So I have to go get iRoutes again, and I have to join it on airports where my airport destination is the airport code. And then I'm going to select the sources from my target. You can go through this SQL on your own. Trust me, I took no joy in writing this. Okay, so, oh, it copied in twice. That's great. Oh, I'm going to get the counts here. This is what this one is. I'm not going to worry about the counts right now. Okay, let me just delete that. Okay, so let's give this a run. Okay, so where all can I get if I feel like playing, taking 2 planes from Denver? And I wind up with a whole big list of things. You can go through it on your own. Put your favorite airport in there on your own. So that's doing exactly 2. Okay, but now let's say I want to get 1 or 2 hops. Now, what you're going to see, I mean, spoiler alert here, is that this is really easy within a graph database. But let's look at this SQL query. Again, the file that I'm looking at is in the SQL directory, the workshop subdirectory, and this is called 1 or 2 hops. Did I get the right one? Just make sure I did that correct. Okay. So 1 or 2 connections of Denver. So I get my 2 hops, which is basically the same query as before. I get both hops, meaning, so I've got exactly 2 hops here. And then I have some that appear as 1 hop. I can get directly there. Like I can get directly from Denver to Chicago, or maybe I go Denver to Houston to Chicago. So I get all of those. And then I'm going to get all the distinct ones where the destination is not Denver. So I don't want to fly Denver to Chicago to Denver because that would be silly. Okay, so here I go. I've returned my destinations. I didn't return the city this time, but I think you get the point. I can get to a lot of places from Denver. Cool. Okay. Now we're going to get a little complicated. And to do that, I want to show a slide here. So let me get back to my slides. We are going to do what is the traditional PageRank query. Now, I've copied this straight out of the GDS API docs. But essentially what PageRank does is it looks at the importance of a node. It calculates the importance of a node based on the number of nodes that come into it. There's a little bit more to it than that, though, which is that it has to look at, are there important nodes coming in versus not important nodes that are linking to it. This was the algorithm that was written by Larry Page that became the basis of early Google. And so, for example, let's say I have my GitHub page, and I've got a bunch of people who've put a link on their GitHub page to my GitHub page. And that's all cool. But let's say Barack Obama has GitHub and Barack Obama links to my GitHub page, but a lot of people link to Barack Obama. So Barack Obama's GitHub page is really important, but Barack Obama links to me. It's all about who you know, right? And that's what PageRank does. My PageRank would increase because Barack Obama linked to me. That's how PageRank works. It's an iterative thing, and there are some hyperparameters associated with it, such as this thing called a damping factor. We have to look at in degrees. We have to constantly update our page rank to determine, well, okay, so my GitHub page, but now I have to go calculate how many people linked to Barack Obama's GitHub page. We run this over several steps. Okay, and that's what we're going to do today is we're going to write this in SQL. Now, this is kind of cheating. I have provided you with the query because let me tell you how unpleasant it is. Okay, so you're going to go into, again, SQL workshop queries, and then PageRank is the name. I will tell you that I looked forever because I will be honest, I did not write this one myself. I looked forever to find somebody that had an example. And there's basically one example out there, and everybody links to this one example. Oh, yes, you can do it. Here's how to do it. And it links to Stack Overflow. One person wrote an answer to one question in Stack Overflow using T-SQL, and that's what everybody uses. Now, I took that query and I rewrote it for Postgres just because I like Postgres better. And it's massively unpleasant. So I'm copying it in right now. First off, like just looking at the fact that it's 93 rows should make you go, oh. Okay, so this is what the query looks like. We're creating some temporary tables. Out degree. This is the page rank is based on out degree. I have a main table that I'm going to create here called PageRank, but I have to constantly update my PageRank through that iterative process that I was talking about. So there's this temporary table. Let's see. Okay, so I'm going to create a table called out degree, and it's just like the in degree thing that we did before. It's just the opposite. We did it in that complete degree query. Okay, so here is my table. I want you to just keep track of the number of joins here. I've got my left outer join. Okay. All right, now I've got some looping that must occur here. This is how we're going to get started with our PageRank loop. Now I'm setting some hyperparameters here. This is alpha. That's that damping factor from the PageRank calculation. And I'm just going with what the default is in GDS when GDS does this, which is 0.85. We have to have this concept of node numbers, how many nodes are within my airports. How many airports do I have? Because that's a scaling that determines how PageRank is going to work here. Okay, so then I begin my loop, and I am going to be, I start off with this idea that my rank is just this equation here, 1 minus alpha over the node number. Okay, and okay, now I've got another join. Okay, I'm joining it without degree. Okay, and then I iterate. Here's another begin loop. Okay, that's not going to help us on speed either. I'm going to do less than 20 iterations, and that's roughly, I think, what's in GDS. And then I just keep updating my rank into this temporary rank. Okay, now think about if you were doing my PR review. Okay, first off, you would hate me. Secondly, how do you determine this is getting the right answer? I have no idea. Okay, so I end all of my loops, and then I go and I get my page rank. Oh, wait, here's some joins. I got 2 inner joins here. Did I miss any joins? I must have. Yeah, here's 2 inner joins up here. Okay, got a lot of joins. Remember, that was one of our big hints on do I have a graphy problem is do I have a lot of joins? The answer here is yes. Okay, and I mean, truly PageRank is a graph calculation. So this is almost not fair. But I'm just trying to make a point here, which is how unfun this calculation is. And I run it, and there it goes. So I can see I've got some prioritization here, my page rank. And don't get really wound up about what these exact numbers are. Every different iteration, every different version of PageRank calculations has slightly different scaling, okay? Really, when people do PageRank, the thing that they care about is what's the order, all right? Okay, that was PageRank. So I hope you took away from that 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 was not fun. All right, let's start looking at this in a graph solution. So we're going to use Neo4j Sandbox. These are free database instances. Some of them are pre-populated, but there's a few that are not blank sandboxes that we can use. So if you go to sandbox.neo4j.com, that's where you're going to find this. And I can scroll through here. Those of you who are asking questions about where to learn, you can see this movies database here. It says it's beginner. That's a great place to start. As you progress, the next place you want to go, if you're a data scientist, is this thing called Graph Data Science. It's again for beginners. That's the one that's being updated shortly, but it's currently the Game of Thrones data set. Okay, and we've got some, really fun graphs like the ICIJ offshore links. I've got all kinds of different ones in here. I've got pre-built data, but I want you to scroll down and you're going to look for this one called blank sandbox dash graph data science. Okay, that's what you're looking for. So I click it. Okay, and then I'm going to hit this button on the lower left called create. Okay, and it's going to spin up an instance for me. Okay. They're limited in duration. I think they last for 3 days and you can extend it for, a handful of more. Okay, so now I have an instance. I am going to click this open button. Okay, open with browser. And what this is going to do, it's going to create a new tab in my browser. I find if I don't click away from this new tab, it loads it up faster. One of the things, you might get like a bad gateway error, or maybe you just see a blank screen without this green scrolly thing going by. Refresh. Sometimes it doesn't spin up immediately. So that's just like a little gotcha there. Okay. So it takes about a minute to spin up. While it's doing that, I would like to direct you. Okay, there it is. Okay, we're now going to go into the folder in the repository called Cipher Queries. Okay, and within Cipher Queries, there is the file called populatedb.cql. That's one of the common extensions used for Cipher queries, Cipher query language. And I'm just going to copy and paste that whole thing in there. Now, I'm not going to spend a lot of time discussing how this works because I want to show you more data science type things here. So I'm just going to copy and paste it in here and let it run. And it's going to take a second because it's going out and grabbing these CSV files from GitHub, and that can take a varying amount of time based on how GitHub is responding. Okay. So you can see there's like this little spinny wheel over here. If you get an error, you might get like a timeout error. Just rerun this thing and, hopefully it catches you on the next go around. Okay, I got all check marks, so life is good. Let's just take a look here. I'm going to click on this database button. Okay, and I can see I've got 8,627 nodes, and those are spread across airports, cities, continents, countries, regions. And I have almost 74,000 relationships. You remember that graph model that I showed you before? Let's just take a look at this really fast. So it's call DB schema, and then there's visualization right there. I just want to make sure this looks like that figure that I showed you, and it does. I can pull these apart and show it a little easier. Okay, so that's what I expect that to look like. So cool. Let's just quickly look at what some of our nodes look like. So if I clicked that database button again, I'm going to click on this airport thing that's kind of like a teal color, and it's going to give me 25 airports. This isn't a real useful thing to look at. I'm going to click on this table button here so you can see what data is in here. Okay, so I have a label of airport. That means that my node is type airport. And then I've got a bunch of properties. And this is all in the CSV file. I've got the altitude. I've got a description here. Longest is how long is the longest runway. IATA, that's the airport code. So Atlanta has an airport code of ATL. ICAO, sometimes that's a different airport code designation. Some people use that one. I've got latitude and longitude. I've got 5 runways. So that's just what's in my airport nodes. And you can click on others of these, like here's continent. Continents have codes associated with them. So that's all cool. All right, now let's get into doing some actual data science on this. Now, this is where we're going to start using the notebooks. And what I'm trying to do here, I'm showing you a whole bunch of different ways to interact with different things. There's no right way to do this. There's no good way to do this. But because we're data scientists, we like doing things in notebooks. We like using things like Python. So I'm going to show you how to do that. Okay, so I'm going to create a Colab notebook. If you want to use Jupyter, it's cool. It's all going to look the same. Just go into that notebooks directory and you can use those in Jupyter. But let me show you how to do this in Colab because I think it's pretty cool. Okay, now I've got a blank notebook here, but what I'm going to do is I'm going to click File and then Open Notebook. And I'm going to open it from GitHub because we're going to pretend that GitHub is working today. Now it says enter a GitHub URL or search by organization or user. Now I'm going to search by CJ2001, which is me on GitHub, / graphy_problems. That's the name of the repo. Click enter here. Okay, so it knows where my notebooks are within that repo, which I think is really cool. Okay, so we're going to start with basic queries. And what I can do, if I scroll over here, you can see that I can open this in a new tab. And I'm just going to do that. It's going to save us some time later when we open the second notebook. And here we are. Here is my notebook. Now I've tried to comment this up a fair bit so that if you're not running the code with the course, that you can still run it and understand. I've also left in what the answers are, what the outputs are, just so you can get a feel for, is your code properly running. All right, now if you're in Colab, it does not actually possess the Neo4j driver in it. So we have to install that. And the way we do that is we use ! or bang pip install Neo4j. Okay, I hit Shift Enter. Oh, it's not authored by Google. I trust myself to run it. Okay, so it's installing the Neo4j driver right now. It has some of the more popular data science packages like pandas in it, so you don't have to install all those. It's just the more custom packages that you have to install. Okay, so we've installed it now. So I can import it. I can import pandas. Okay, cool. Now we need to connect to our sandbox instance. And in order to do that, we need to know the IP address of the instance as well as the password. Now I'm going to show you where to get that. I go to my sandbox UI. Okay, this is where we told it to open our new tab. And I click on this tab here called Connection Details. You'll see here I have Bolt URL. This is the IP address working off of the Bolt protocol, which is appearing on port 7687. So I'm going to copy that to the clipboard. Go back into my notebook here. And I have a class for establishing my connection. There's all kinds of different ways to do this, and I'll tell you right now it's changing. We're updating the Python driver, and we're also creating some special wrappers for GDS around it. Those are going to be coming out very soon, like, I don't know, tomorrow. So this will probably I'll probably update this stuff, but for right now, we're using GDS 1.8 in case you're curious. So I'm just going with the traditional way of doing this. Okay, so in this cell, I have this thing called URI, and I'm going to enter that Bolt IP address there. Now, I need the password, so I'm going to go back there. These passwords are always 3 words separated by dashes. Okay, so I'm going to copy that to my clipboard, go back to my notebook, put that in there, maybe. Okay, so here's where I establish my connection through that Neo4j connection class that I have. I tell it what my URI is. I tell it what my password is. The username is always Neo4j for a sandbox. And then I always get a warm fuzzy if I tell it, just tell me how many nodes are within my database. Now, let me just tell you what this means here. If you're new to Cypher, matches select in SQL. Okay, so it's just think match equals select. Okay, and then anytime you see round parentheses, that is a node. Okay, square brackets are going to mean relationship, but round parentheses mean nodes. So I'm going to match all of my nodes here. I haven't specified a node type or anything. Just give me all of my nodes and return the count. So this is like in SQL, select star from table. Okay, and I'm going to return it as a new column named count. So let me run that. Okay. When you do this, there's two different ways that the results will come back. You can get it back with something that looks like that, which I don't find very helpful. Or if I use, some array indexing notation, I can just get that back as an integer. Cool. Okay. Now let's count the number of relationships. So remember I said that round parentheses, that indicates a node, and square brackets indicate a relationship. So here's what I'm doing here. This is kind of like ASCII art. It's kind of cool. So you can see here, I kind of have an arrow, right? So I've got a node with an arrow to another node. So I have a node with a relationship to another node. I don't specify which relationship that is. This was similar to just putting some n in here. I'm just saying grab me all relationships, and it's putting it into a variable named r, and I'm counting them just like I did before. So I give this a run, and I get that there are 73,954 relationships, which if I go back here into Sandbox, that's exactly what I get for my number of relationships. So that's good. We're making a good connection between Python, notebooks, and our database. Nice. Okay. Now, you remember before we looked at the in degree of flight routes. We did this in SQL. And that was in the SQL folder, workshop directory subfolder, in degree. Now, it's not overly complicated. Okay, here it is. Okay, that's not a very complicated query, right? Let's talk about how we do it in Cypher. Okay, so now this might look a little bit more complicated, but trust me, as we get into the complicated SQL queries, this gets a lot easier. So here's what I'm going to do. I'm going to match my airport nodes. So remember, round parentheses means a node. And in this case, I'm specifying that my node is of type airport, or it has the label of airport. I'm assigning that to a variable called A. Now, so this is like, select star from airports. With my airport, okay, so I'm returning that match into a new statement here. So think of that like a common table expression. Okay, so with my airport, I have the size. Now, the size here, let's look at what this means. I am returning some node has a route into my airport. And the size is just telling me how many of those things there are. So I'm returning that size as in degree. And I'll return the name of my city and the in degree. I'll order it by in degree descending. I'll limit it to 10. Okay, so let's give that a run. And what do we get? Okay, first off, let me point this out here. I feel like working with a pandas data frame as opposed to just those integers. So I'm creating a dictionary of those returned results. So I run my in degree query, and for everything in that query, I'm creating a dictionary, and that dictionary is being put into a data frame, and I'm going to return that data frame. And here's what I see. Okay, so we did out degree before. No, we did in degree. Okay. So yeah, this is pretty similar to what we had in our SQL query. So cool. All right, let's scroll down a bit. Here's our total degree. And all I've done here, the only difference between total degree and in degree, you see I have my arrow relationship going towards my target. Now I'm going to break that. I'm not going to have the arrow relationship. I'm going to have no arrow here. So that means that my relationship can go in either direction. You see there's no pointy greater than symbol here. So let's just give that a quick run. Excellent. Okay. All right. Now, you remember before we were looking at one hop, two hops, one or two hops, and you remember how not fun that was to do in SQL. Let's do that in Cypher. Okay, so this first one is my one hop query. So I'm going to match an airport. Now you see my squiggle braces here. Um, and what those are is I'm setting a property for my node. And in this case, I'm setting that the IATA code is Denver. This is just like doing a SQL select star from airports where IATA equals Denver. Okay, so that's the same thing. So I have my directional relationship. So it has a direct route to some other node. Okay. And I know that's an airport node. I probably should be more specific and put colon airport in here just so it doesn't, it's more efficient to say you're only looking for the airport nodes, but we're just going to go with this for now. Has route is a relationship that's only between airports. So, that kind of helps. All right. So that's my one hop query. My two hop query, if I want exactly two hops, okay, what I do is I say has route times 2. Okay, so that times 2 means 2 hops. Okay, and I'm going to return the count of those. And then the last one is the 1 or 2 hop thing. So star 1 dot dot 2, that's the way 1 or 2 hops. Okay, 1 to 2 hops. All right, let's give that a run. Okay, so here's how many airports are 1 hop, 2 hops, and 1 or 2 hops. And because those numbers are so close to each other, the 2 hops or 1 or 2 hops, it just reflects the fact that Denver is a hub airline or hub airport. So you can get a lot of places with my different number of hops. Now, what I want you to think about is we have done this demonstration now for just 2 hops, but I call this the 6 degree of Kevin Bacon query. For those of you not familiar with it, there's the actor Kevin Bacon, and they want to find all of the actors that are within 6 hops of Kevin Bacon. Now, all I have to do with this query, and it's not going to be very instructive, but all I have to do here is replace the number 2 with the number 6. That's as simple as it is. Now, think about what that would look like if you did that in SQL. Okay. How many joins do you have? How many common table expressions do you have? The answer is a lot. Okay. This is a graph problem. Use graph tools for graph problems. It makes it simpler and it makes it faster. Okay. We're going to do one more notebook here before we're done. Okay. And this is going to demonstrate some of GDS. Okay. So this is called Graph Data Science, this notebook here. We're going to open it in a new tab. Okay. Now, again, I'm going to have to install, because I'm on Colab, I need to install Neo4j's driver. Yes, yes. Okay, so while it's installing that, we're going to come back and we're going to have to repopulate our IP address and all of that to make our connection. Okay, you done yet? There, we're done. Okay, I'm going to bring in my packages. I am going to create my connection class, and we know I'm going to have to tell it what my IP address is. I'm going to go back and get my password. Put it in here. Oops. There we go. Okay, and again, I can see that I get the correct count of nodes, so I'm happy with that. Okay, now, when I am using the Graph Data Science library, the thing that happens here is that you create these things called graph projections, and what they are is an in-memory representation of the things that you care about in the graph. You may not care about every single node within this graph or every single relationship type, so you don't always want to throw everything into these in-memory projections. The projections, what they allow for is very fast, efficient computation of some of these more sophisticated algorithms. But I have to create that in-memory graph first. And that's what's happening here with this gds.graph.create. Now, I told you that we're working with GDS 1.8. This is one of those syntactical things that changes in 2.0, is that instead of graph.create, it's graph.project. Okay, so this is going GA tomorrow. It's going to be a little bit before it hits Sandbox, but just know that that's coming. Okay, so the syntax here, I give my graph a name. I'm going to call it routes. And I have to tell it what nodes and what relationships do I want. So I want my airport nodes and I want my has route relationship. Okay, so I'm going to run that. I'm just returning some information from that query. So, we could do this within Sandbox as well, and it would give you all the same information. Okay, now let's do PageRank. You remember how not fun that was in SQL. Okay, let's now do it in GDS. And this is the entire query right here in yellow. Okay, GDS.PageRank.stream on my named graph, routes. Okay, there are several options here for PageRank. .stream means I just want the information on the screen. .write, what it will do is write that information as a node property in the actual graph database. There's .mutate, .stats. Mutate means put that information back into my graph projection. .stats means, oh, I'm worried that this might take a lot of memory. And GDS can be memory intensive, so particularly the heap. The nice thing about Sandbox is that you don't need to configure that stuff. And so, but if you are at all worried that you might be running up on memory issues, you'd want to use .stats. Okay, so when things are stored in these graph projections, they're not stored in things that we would recognize. It gives it an arbitrary node ID. It doesn't correspond to anything really physical that we would recognize. So I need to turn that into something that I care about. And that's what this gds.util.asNode does, is it takes that node ID and I want the property of IATA out. Okay. And then I'm also going to get the description out. That's the description of the airport. So like Hartsfield-Jackson Airport. And then score is the name of the PageRank as it's returned from this algorithm. So I want to also return my score. I'm going to order my score by descending. I'm going to order it by descending PageRank and then ascending IATA code. And I'm going to, again, return that in a data frame. Okay, so let's give that a run. All right, and that's done. Here we go. Okay, now these are slightly different than the results that we got in SQL, and that's probably having to do with number of iterations, and some hyperparameter settings are different than, I just wrote I creatively open sourced a very basic PageRank query. There's a lot of math that happens under the hood in GDS. And the nice thing about this, though, is that I am not having to write this, this complicated PageRank SQL query. There's all kinds of really sophisticated things that GDS does. It handles clustering natively. So to try and create clusters within SQL, there's a popular method called Louvain's method. Look, that's a community detection method. I don't even want to think about how to do that in SQL. And there's just all kinds. Really go through the GDS API docs. It's really impressive the number of algorithms that are in there, and it also includes some pipelines, machine learning pipelines for node classification and link prediction. So you don't have to write those yourself if you don't want to. If you want to pull it down and pull the embeddings down, oh yes. GDS has the embeddings calculation. We talked about FastRP and Node2Vec. There's another one in there called GraphSage. So all of that stuff exists within GDS, and it's a really great thing. Anything that you can do in GDS, anything that you can do before sucking your data into Python, it's generally faster and more efficient. And again, you don't have to write it yourself. It's already there. Okay, this is how I'm going to write my PageRank to my nodes. Remember, I had .stream before. Now I'm going to use .write. I'm going to tell it that the property is called PageRank. Okay, so we're going to give that a run. Okay, so I can see that it wrote node properties for 3,503. Okay, all right. Here is something that I challenge you to do in SQL, which is the shortest path. Let's say I had a source node and a target node. And you remember that my routes table has distances between nodes. And I want to find what is the shortest path to go from my source airport to my target airport. So let's do that. In this case, we're going to use a weighted graph. I did not, in our original graph, pull in the distance, but now I'm going to do that as a relationship property. Looks pretty much the same otherwise. So I'm just creating a new graph projection. Okay. Now, I was fantasizing the other day that living at the source node of Denver, I would really love to go on vacation. And you can't see it here because for whatever reason, the screen isn't updating. But if you look at the actual notebook someplace other than within, let's see if I can just zoom out for a little bit. It's not going to refresh. Or maybe it did. Okay. I really want to go to the Maldives. This is the Maldives airport code. Malay is the name. I'm not sure I'm pronouncing that right. So my source is Denver. My target is Maldives. Okay, so I'm matching on both of those. And then I'm going to use this algorithm that's built in to GDS, and it's Dijkstra's shortest path. Okay, so this is, and again, don't ask me the proper pronunciation there. I apologize. I don't actually know. I'm going to stream this to the screen. Okay, using my weighted graph. I have to tell a source node, and I have to tell it a target node. And my weight property, my relationship weight property here is distance. You can go through this and read the API docs. We're running short on time, so I'm just going to cruise through this really fast. But just take a second and think about how would you write the shortest path between two airports in SQL? In those, you'd be using the iRoutes table and you'd be joining on it several different times. It would be very much not fun. And you can't assume that, okay, if I want to find the closest airport to Denver, it's probably Colorado Springs. But Colorado Springs is not necessarily on the true shortest path to the Maldives. I'm pretty sure it's not actually. So let's give this a run and just see what I get. Okay. So my source node is Denver. My target node is Maldives. I can see that the shortest distance, and I believe this is in miles, is 9,700 miles. And here are the airports that I hop through. Now, this is not exactly going to be the best way to get to the Maldives. It just happens to be the geographic shortest path. Okay. So this is like Helsinki, and one of these is Moscow. I can't remember what KEF is. So yeah, doing that in SQL would be massively unpleasant. Let's do clustering. Okay, remember I said we could do community detection. It's clustering within the graph. So think about that coronavirus graph that I showed, and we had red sections and yellow sections and green sections. And this is basically looking at which nodes have a lot of relationships with which other nodes. Okay, so again, I'm not using the weighted graph for this one. I mean, you could if you wanted to, might make sense. But let's return this. Let's run this really quick. And what you're going to see, it's going to take it a second. This is a bit more computationally intensive. If you go through these results, if you run this for yourself, what you'll see is that clusters here, I get a lot of my first community here, and these are arbitrary integers assigned to my community ID. I have 695 airports within that community. And if you go through it, they all happen to correspond to airports within the United States and North America, whereas this next community tends to be European. I've got some of the Asian airports here. You'll see London and London. One of these is Heathrow. One of them is Gatwick. So yeah, that's looking at the communities in the graph. And then I can look at which nodes are most similar. I'm not going to run this right now, but what you'll see, and this is go through the GDS docs on this, but if I'm looking at the most similar airports to Santa Fe in New Mexico, I'm getting that other airports within the desert Southwest are most similar. So yeah, just there's so many things, so many data science things that you can do within the GDS library that you absolutely cannot do within SQL. Why? Because it's designed around the graphy problem. Again, we're going to go, we just keep hitting on this. Do graphy work in a graph database that's truly set up to do this? So we're going to wrap up now. I want to remind you of the two key concepts. First, it isn't always obvious that you have a graphy problem, but if the relationships matter, if you have multiple SQL joins, those are your big hints. It's easier and faster to solve graphy problems in a graph database rather than a relational database. I hope that is something that you've gotten to see today and taken away from today. Final thoughts. SQL is all right. It can be just fine if you have basic queries, you don't have relationships between individual data points, that's all fine. SQL, I'm not going to tell you not to use SQL. I'm not going to tell you that SQL is the wrong tool for everything. It's not true. But like I said, if you have more than a few joins, you have a graph. We know that graphy problems benefit from graphy solutions because graphy solutions are faster, easier to write, take advantage of the relationships between the data points. All right, we have come to the end now. I just want to say thank you again for attending. Thank you, Alex, for hosting. I am really happy to have been able to be here. This is where to find me on Twitter, CJ Loves Data 1. Please reach out to me there if you have questions, comments, feedback. Please, if you want to, go create issues and pull requests within the repository. I love getting those. So with that, I am going to stop sharing my screen. Again, hit us up on Discord too. I'm on Discord as well. So that's it. Let's see if we've come to the end of time, but we can stay. I can stay a few minutes later and answer some questions, or again, feel free to do them on Twitter.
Thank you very much, Claire. That was cool. Whirlwind at the end, but I think we got there. And as we mentioned previously, right? I mean, this video is available later on, so you can watch it and then click on pause. But I also think the repo is great, so everything is in there. So if you're really stuck with something, you can always read up on that in that repository where everything is available. So I think it's super good. We can, maybe we can do one more question before we close. And again, like you already said, community Discord is open. So if you have any follow-up questions for later on, for afterwards, if something comes up, either hit us up there or hit Claire directly on Twitter with some questions. That's also possible, I guess. So, but ideally, you go to community or Discord for your questions.
Yeah, and I do like using community or Discord because chances are if you have the question, other people do too. So if you're sending me private messages like on Twitter or something like that, not everybody's going to get to benefit. So definitely those are preferred ways, at least in my view, for reaching out to us.
Yeah. Maybe one question that came up in chat, and I think that's maybe interesting for people. What's the difference between, or is there a difference if I use Neo4j Community Edition versus Enterprise Edition with the Graph Data Science section?
Absolutely. Love that.
Yeah.
Yes, there is. With Community Edition, you are limited to 4 cores. So, your computational power is reduced. And with Enterprise Edition, you basically, what do you need? Set up what you need. So how many cores? And if you are using, this is analogous. If you're using Aura, we have Aura DB, Aura database. It does not have GDS on it, but stay tuned. There might happen to be something coming out very soon as a data science solution for Aura. But Aura is a completely managed solution, and you can specify in there, like there's a free version, and it's obviously got limitations because it's a free version. But like if you've got a bigger graph that you need to chunk away on, you can specify I need an instance that's X number of CPUs and Y amount of RAM. So yeah, but the Community Edition is a great place to get started. The Sandbox is a great place to get started, and Docker. I have some Medium posts on how to use Docker, and there's a bunch of repos that I use Docker to set up Neo4j as well. So yeah.
Cool. Perfect. I think that brings us around for today. Thank you again, Claire, for giving the demo and for all your work with the repo. I think that's very insightful and helpful for everybody. Thank you for watching and for attending today. Thank you for making it lively with your questions. Sorry if we couldn't answer your question. I think Tomasz, thank you again. Also, a shout out to Tomasz for chat support.
Definitely.
We try to answer as much as possible, as many as possible. If there is, if there was no time for an answer to your questions, don't be sad. Take it to the forums, and there will be plenty of time to answer the question there. Thank you for watching again. Have a great rest of your day wherever you are. Good rest of your week. Take care, everybody, and we hope to see you soon in the future.
Bye, everyone.